All right, so conventional biological wastewater treatment processes require oxygen. And let's get into a little bit more detail about the specific oxygen requirements of these processes. So we can conceptualize oxygen demand for wastewater treatment based on this stoichiometric relationship that exists between the organic compounds that are being removed by the bacteria, the amount of oxygen the bacteria are consuming during aerobic biodegradation of this organic material. And as a byproduct, those microorganisms are producing new microbial biomass. So this chemical formula here, this compound does not represent an entire microbial cell, but it's the proportions of carbon, hydrogen, oxygen, nitrogen, and phosphorus that you would find in microbial cells. And they're also producing carbon dioxide from the oxidation of these organic compounds. And so we have here CH2O multiplied by X. Now that's kind of a generic representation for the vast diversity of organic compounds that you'll find in domestic wastewater. The most common approach to define the fate of substrate, in other words, these organic compounds, and the oxygen requirements to degrade the organic compounds, the most common approach used is the COD balance. So we use COD, which is chemical oxygen demand. We use that because it can be defined in terms of an oxygen equivalence, right? So when you see these stoichiometric equations, keep in mind that we're taking into account the production of microbial biomass. Bacteria in these wastewater treatment systems are constantly reproducing. They're producing new microbial cells. And we can represent that microbial biomass as a chemical compound proportional to the amount of carbon, hydrogen, oxygen, nitrogen, and in some cases phosphorus that we find in those cells. So this C50, H70, O20, N10, and P1 is one way to represent it. If we were to ignore the transformation of phosphorus during these processes, we can simplify this to C5H7O2N. So this is a common compound used to represent microbial biomass in wastewater treatment systems. All right, so C5H7O2N. Whenever you see that, you should just think about microbial biomass sludge from wastewater treatment processes being produced. And it's based on the chemical composition of a microbial cell, right? So microbial cell is 70% water, H2O, which is where we get a lot of the H and a lot of the O. It's 30% chemicals, and those 30% chemicals consist of proteins, which you can see here, have carbon, nitrogen, hydrogen, oxygen, 4% small molecules, also RNA, phospholipids, DNA, polysaccharides. You can see DNA, RNA, some of those elementary molecules that make up nucleic acids, also, of course, have carbons, hydrogens, nitrogens, and oxygens. All right, so these are the four most important molecules when we talk about microbial cells. The oxygen requirements using stoichiometry. So let's assume that the organic matter in wastewater can be represented as glucose. So we know that wastewater contains lots of carbon compounds, complex, long chain carbon compounds, carbohydrates, sugars, but let's just assume that everything is glucose. All right, so C6H12O6. And again, we're representing our new microbial cells being produced in the reaction as C5H7O2N. So the stoichiometric equation can be written as follows, right? Balanced equation, we have the oxidation of glucose to CO2, and also the production of new microbial biomass, utilizing oxygen as an electron acceptor and consuming ammonia in the process. Microbial yield, which we represent using the variable y, is based on the glucose consumed can be calculated as follows. And we're going to use volatile suspended solids as a way to represent the mass of microbial cells. All right, so yield is a representation of the mass of microbial cells produced per mass of glucose being consumed in this case. All right, so we know that the molar relationship between biomass and glucose is 2 to 3, but we use the molecular weights of those two compounds to convert this to a mass ratio. Again, the C5H7O2N is microbial cells, so it's the grams of cells, and we measure this in wastewater as VSS usually, volatile suspended solids. And that's grams of VSS per gram of glucose. So here, based on this stoichiometry, we can see that the yield is equal to 0.42 grams of VSS per gram of glucose. That's how much microbial biomass we're going to get for every gram of glucose being consumed. All right, so 0.42 grams of bacterial cells are being produced for every gram of glucose or food being consumed by that bacteria. Let's use an analogy of humans. Right, so let's say a human over the course of 25 years consumes a total of 50,000 pounds of food, right? And another human, same thing, over the course of 25 years consumes 50,000 pounds of food. Those two humans have an offspring, two new humans. Let's say they have two offspring, two new humans, so they replace themselves with two new humans, each 10 pounds. And essentially the analogy here is that 20 pounds of new humans are being produced for a total of 100,000 pounds of food that has been consumed. That's a ratio of 0.0002 pounds per pound or grams per gram. So compare that to bacteria. You can see bacteria produce biomass much more efficiently than humans do, based on the amount of food, if we normalize it by the amount of food that they consume. All right, so yield, this concept of yield is very important when we talk about wastewater treatment, biological treatment, and design of biological treatment processes. In practice, again, we use COD to represent the organic matter, and we use volatile suspended solids to represent the new cells. Right? These are two laboratory analyses that are done on a routine basis at wastewater treatment plants. The COD of glucose can be determined also just based on the stoichiometry. All right, so chemical oxygen demand is roughly equivalent to what we would call the theoretical oxygen demand. And the theoretical oxygen demand of glucose can be calculated as the mass of oxygen per mass of glucose in this stoichiometry, which is showing the oxidation of glucose to CO2. So the COD of glucose can be calculated to be 1.07 grams of oxygen for every gram of glucose. Theoretical yield in terms of COD is then calculated as follows. All right, so if we look at the yield, the grams of C5H7O2N per gram of glucose represented as COD, right? We get 2 moles of C5H7O2N at 113 grams per mole. We have 3 moles of glucose at 180 grams per mole. And again, the molar relationship between microbial biomass and glucose that we saw in the previous slide was 2 to 3. However, here, the difference is that we're converting that glucose to a COD equivalent. Instead of grams of glucose, we're representing this per gram of COD or per gram of oxygen needed to produce that microbial biomass. So we see here that 0.39 grams of bacterial cells are produced for every gram of COD that's being degraded. In other words, every gram of oxygen that's being consumed in the reaction. All right, so oxygen needed for COD balance, the quantity of oxygen utilized can be accounted for by considering oxygen used for the substrate oxidation of those organic molecules to CO2 and producing H2O as a byproduct. The COD of the biomass, which is the amount of oxygen that's incorporated into the microbial biomass, and the COD of any remaining substrate that has not been degraded. So the oxygen equivalent of biomass, C5H7O2N, can be found by representing the stoichiometry of the oxidation of this biomass. All right, so if we were to oxidize C5H7O2N to CO2, this is the balanced stoichiometry. And if we use our calculation of grams of oxygen for every gram of biomass, you can see that we get 1.42 grams of oxygen needed to oxidize each gram of microbial biomass. All right, so keep that number in mind, 1.42 grams of oxygen per gram of VSS. The oxygen required based on a COD balance is calculated as followed. So if we look at how much COD is removed in a wastewater treatment process, this is equivalent to the amount of COD that's oxidized. In other words, the amount of COD that's converted to CO2 and escapes the system, plus the amount of COD that's bound up in the microbial cells that are produced. Because remember, those microbes are degrading COD to conserve energy, to produce energy for themselves. And they're also degrading that COD to incorporate it into biomass. So we have the COD that's used to oxidize organic matter to CO2, and we've got the COD that's used to produce new microbial cells. All right, so COD removed equals COD oxidized plus COD of cells. We rearrange that equation to calculate the COD that's being oxidized. We get this form that the grams of oxygen consumed in the reaction divided by the grams of COD, and in this example, we're still imagining that all of that COD is present as glucose. And that's equal to COD removed minus the COD from the cells. So based on the previous slides, we know that the COD removed has an oxygen equivalence of 1.07 grams per gram, right? 1.07 grams of oxygen for every gram of glucose. If we multiply that by the 3 moles of glucose in the reaction and the 180 grams per mole of glucose, the moles cancel out, the grams of glucose cancel out, we're left with grams of oxygen based on the COD removal. All right, so this term right here calculates the mass of oxygen for COD being removed. From that, we're going to subtract the COD that's tied up and incorporated into the microbial biomass. All right, so remember that 1.42 grams of oxygen that's tied up in every gram of VSS for microbial biomass. So we take that ratio and we multiply it again by this term here, 2 moles of C5H7O2N times 113 grams per mole. The moles of C5H7O2N, moles cancel out. Grams of VSS or grams of C5H7O2N cancel out. And we're left just with grams of oxygen that's tied up in the microbial biomass that's produced as sludge during the wastewater treatment process. All right, so we take these two terms, subtract them, and we get 0.44 grams of oxygen for every gram of COD that's being removed in this reaction. We can also calculate the same thing just using the stoichiometry. So if we return back to the stoichiometry, right, we saw this in the previous slide, 3 moles of glucose plus 8 moles of O2 plus 2 moles of ammonia is converted by microorganisms into new microbial biomass, specifically 2 moles of C5H7O2N plus 8 moles of CO2 plus 14 moles of H2O. All right, so based on that stoichiometry, if we calculate the grams of oxygen being consumed in the reaction, that's 8 moles times 32 grams per mole, and we divide that by the grams of COD as glucose being consumed in this reaction, right? That's 3 grams of COD times 180 grams per mole. And then we convert that to an oxygen equivalent to get it in terms of COD, 1.07 grams of O2 per gram of glucose. This ratio gives us the value 0.44 grams of oxygen per gram of COD. Same thing we get with the calculation done above. All right, so this is the oxygen needed for COD balance in this reaction. Let's do an example problem. All right, so take a look at this figure here. This is showing a schematic of a biological treatment reactor. Right, let's say this is an aeration tank for a wastewater treatment process. So we're pumping oxygen into the system. We've got a flow of wastewater coming in that has COD in it. So we've got a mass of COD entering the system. We've got some of the COD, which is not degraded, exiting the system, right? So there's going to be a COD removal between the influent and the effluent. And we've got the production of microbial biomass. So we've got these volatile suspended solids that are produced inside this reactor, which are leaving the system. The COD that's consumed by the microbes, in other words, the organic carbon compounds that are consumed by the microbes are converted, a portion of it is converted to CO2, and a portion of it is leaving as VSS, as microbial biomass, right? So we've got this flow of organic molecules, some of it going to CO2 and some of it going to microbial biomass in terms of VSS. All right, so we can do a mass balance around this reactor and use that mass balance approach to perform these calculations in this example. All right, so this is an aerobic, completely mixed biological treatment process with no recycle. All right, we're going to get into systems where the biomass is recycled in a return sludge flow that's typically seen in activated sludge processes. But for this example, let's assume there's no recycle here. This treatment process is receiving wastewater with a COD concentration of 500 milligrams per liter. So the flow rate is 1 million liters per day. The reactant effluent has COD and VSS concentrations of 10 milligrams per liter and 200 milligrams per liter, respectively. So part A, what is the observed yield in this system in terms of grams of VSS per gram of COD removed? And part B, what is the amount of oxygen used in this reactor in terms of grams of oxygen per gram of COD being removed? Okay, so to solve this problem, we first have to draw a mass balance around the system, as you can see up here on the top. And the first part of the problem is to calculate the observed yield in terms of the grams of VSS per gram of COD removed. So we know that the VSS concentration coming into the system is negligible. In other words, there are some microbes that are coming into the system. There's some bacteria, but they really multiply quite a bit inside the reactor, so we can consider what's coming into the system negligible. What's leaving the reactor in terms of VSS concentrations, we have 200 milligrams per liter, which is equivalent to 200 grams per cubic meter. We also know that the flow rate is 1 million liters per day, which is equivalent to 1,000 cubic meters per day. Therefore, we can calculate the loading of VSS leaving the system by multiplying the flow rate by the VSS concentration. So we get 1,000 multiplied by 200 is equal to 200,000 grams of VSS leaving the system per day. Now we can calculate the grams of COD removed from the system by subtracting the loading of COD leaving the system from the loading of COD coming into the system. So we know that the loading concentration coming in is equal to 500 grams per cubic meter, or milligrams per liter, and the concentration leaving the system is 10 milligrams per liter. So using the flow rate of 1,000 cubic meters per day, we can calculate here that the grams of COD removed per day is equal to 490,000. So now the last step to calculating the yield is to divide 200,000 grams of VSS per day by 490,000 grams of COD removed per day, giving us a value of 0.41 grams of VSS per gram of COD removed. For the second part of this example problem, we're asked to calculate the amount of oxygen used in the system per gram of COD removed. So we need to use our mass balance approach, assuming steady state, and this time now look at the mass balance on COD, in other words, oxygen demand. So using mass balance, we know that accumulation is equal to the inflow minus the outflow plus conversion, plus or minus conversion, right? And if we assume steady state, then accumulation in the system is zero. There is no accumulation. So therefore, we look at the COD coming into the system minus the COD leaving the system, and the conversion here refers to the amount of oxygen used or converted through the microbial degradation processes, and that's all equal to zero. So we rearrange that equation and we can see that the oxygen used is equal to the COD coming into the system minus the COD leaving the system, which makes sense, right? Because that difference in COD has been created due to the use of oxygen by the microbes. So we calculate COD coming into the system. Again, we're calculating a loading, so we take the concentration, 500 grams per cubic meter, multiply that by the flow rate, 1,000 cubic meters per day, which gives us a value of 500,000 grams per day of COD. The COD leaving the system can now be calculated. There's actually two sources of COD leaving the system. The COD leaving in the liquid effluent, which is a very small concentration of only 10 milligrams per liter, and we multiply that by the flow rate of the effluent, 1,000 cubic meters per day. And then we're also going to add the COD equivalent of the biomass that's leaving the system. Because remember, some of that organic material is being oxidized to CO2 and leaving the system, but some of it is being converted into new microbial biomass, and that biomass has its own oxygen demand, so we need to account for that COD of the biomass. So we know we have 200,000 grams of VSS leaving the system per day based on our calculation that we made in the first part of this problem. We're going to multiply that by a value of 1.42. Now, where does that 1.42 come from? If you recall from previous slides, previously in the lecture, right, we calculated the ratio of oxygen per gram of VSS according to the stoichiometry of a hypothetical oxidation of microbial biomass, right, where we had C5H7O2N representing the microbial biomass. We looked at the complete oxidation of that to CO2 in order to calculate the oxygen demand of 1 gram of C5H7O2N. And we got a value of 1.42 grams of oxygen per gram of VSS. And so if we multiply 200,000 grams of VSS per day by 1.42 grams of oxygen per gram of VSS, we get the amount of oxygen leaving the biomass per day, which is what we want here for COD out. All right, so we sum up those two terms of the COD out calculation, and we get a value of 294,000 grams of COD per day. Next step is to calculate the total amount of oxygen used. We take 500,000 grams per day coming into the system minus 294,000 grams per day leaving the system, which gives us a difference of 206,000 grams per day. The last step is to calculate the ratio of the grams of oxygen per gram of COD removed from the system, so that's 206,000 divided by 490,000, giving us a value of 0.42 grams of O2 per gram of COD removed. All right, so in addition to the oxygen requirements for the degradation of carbon compounds in wastewater, there's also oxygen requirements for biological nitrification. And if we have a wastewater treatment system that has the need to remove nitrogen to meet discharge limits, then we have to account for this amount of oxygen when designing the aeration system. So some of the oxygen is needed for the microorganisms that are degrading the carbon compounds to CO2. And then some of the oxygen is also needed for a different group of microorganisms that are oxidizing ammonia to nitrate, right? And these are the nitrifying bacteria. So ammonia oxidizing or nitrifying bacteria, what they're doing is they're taking 2 moles of NH4 plus, as well as 3 moles of O2, and they're producing nitrite plus some protons, which is going to affect the pH of the solution, and water, 2 moles of water. We've also got nitrite oxidizing bacteria, which are working in conjunction with these ammonia oxidizers. They're taking the nitrite from this reaction and oxidizing it, 2 moles of it with 1 mole of oxygen to produce 2 moles of nitrate. All right, so both of these reactions require oxygen, and we can account for that oxygen in the same way as we've done in previous slides for the oxidation of carbon organic compounds. So if we take these two elementary reactions and we combine them, we can come up with an overall reaction. And just to note, this reaction does not account for the production of microbial biomass. This is just looking at the oxidation of ammonia. All right, so if we combine these two reactions to get an overall reaction, we have ammonia, NH4 plus ammonium, plus 2 oxygen goes to 1 nitrate molecule plus 2H plus H2O. So how much oxygen is required for the oxidation of ammonium to nitrite? All right, we use the same approach. We take the mass of oxygen being consumed in the reaction, that's 3 moles of O2 at 32 grams per mole, and we take the mass of ammonium being oxidized, so that's 2 moles of NH4 plus at 14 grams of nitrogen per mole. And remember, it's convention that we represent the mass and the molecular weight of ammonia, nitrogen, as well as nitrate nitrogen. All nitrogen species we usually represent as grams of nitrogen per mole, as opposed to the molecular weight of the entire molecule. All right, so that's 3.43 grams of oxygen for every gram of nitrogen being consumed in the reaction. For the oxidation of nitrite to nitrate, same thing. We've got 32 grams per mole of oxygen divided by 2 moles times 14 grams of nitrogen per mole. That gives us a ratio of 1.14 grams of oxygen for every gram of nitrogen being consumed in this reaction. If we look at the overall reaction, right, NH4 plus 2O2 goes to NaNO3 minus plus 2H plus H2O. We do the same calculation, that's 2 moles of oxygen at 32 grams per mole divided by 1 mole of ammonium at 14 grams of nitrogen per mole. That gives us 4.57 grams of oxygen per gram of nitrogen. You can see that that's the equivalence of adding up the oxygen requirements from the first 2 elementary reactions. 3.43 plus 1.14 is equal to 4.57. All right, so when we combine 2 elementary reactions into one overall reaction, it makes sense that the oxygen requirements for the overall reaction are equivalent to the sum of the oxygen requirements for the 2 elementary reactions. So now let's get more into the applied part of oxygenation and aeration of wastewater. So oxygen is supplied to a wastewater reactor in what we call the liquid that's inside the reactor as it's being oxygenated. We call that the mixed liquor. That's where the microbes are growing. It's where the COD is being oxidized, or COD is being removed. The organic materials are being oxidized. So we supply oxygen to the aeration tank using submerged diffusers typically. In some cases, mechanical means for different variations of technologies, but for conventional activated sludge, we would use diffusers. And we've got different designs for these diffusers. We've got coarse bubble diffusers and fine bubble diffusers. They've got different properties and different efficiencies for the transfer of oxygen from the air into the wastewater. So this oxygen transfer process is multiple steps. First, the oxygen is in a gas form and it's dissolved from the gas form into the wastewater. And then the dissolved oxygen in the wastewater is taken up by the microorganisms as they're degrading the organic materials. All right, and again, remember we've got oxygen demand coming from BOD oxidation or COD oxidation. In other words, the oxidation of organic material. We've also got oxygen demand coming from the conversion of ammonia, nitrogen to nitrate. And the oxygen demand must meet the peak demand for a wastewater treatment system. Remember that our wastewater flow and also the flow of organic matter into our wastewater is fluctuating throughout the day. And so we need to use a peak factor to account for the fluctuations in oxygen requirements. So sometimes we use a peak factor of 2. You might look into design guidelines for guidance about what type of peaking factor is appropriate for the design. But we can calculate the oxygen demand as the flow rate multiplied by the difference between the substrate coming into the system and the substrate leaving the system. So when I say substrate, I mean that organic material that's coming in, which is food for the microorganisms. From that, we're subtracting the oxygen that's getting tied up into the microbial biomass, right? So this P sub X biological, this is the biological sludge being produced. And remember that ratio 1.42 is the oxygen that's getting tied up into the microbial biomass being produced in this reaction. And we're going to add to that 4.6 times the flow rate times the amount of nitrogen that's being converted into nitrate, because that's an additional oxygen demand. And that 4.6 is coming from a previous slide where we calculated the total oxygen requirement per gram of nitrogen being converted to nitrate. All right, so this PX bio can be broken down into 3 different components, right? There's biomass from the heterotrophic bacteria. These are the bacteria that are degrading carbon compounds into CO2 in the presence of oxygen. We've got cell debris, which is a separate component from the biomass. So cell debris is kind of that portion of the biomass that hangs around after it's not really easily degraded by other bacteria. So when biomass is decaying, some of that biomass is consumed by other bacteria as food. So it's kind of like auto-degradation of bacterial biomass. The cell debris that stays around can be calculated using the second term. The third term is the biomass from the nitrifying bacteria. All right, and that all gets added up to equal P sub X biological, which is part of this equation right here for oxygen demand. All right, so we've got the terms of this equation here defined below. Q is the average daily flow rate, cubic meters per day. Y sub H is the microbial yield from heterotrophic microorganisms that are oxidizing organic materials, COD, in other words. It's typically assumed to be 0.45 grams of VSS per gram of COD oxidized, as we showed before. Y sub N is the microbial yield from heterotrophic microorganisms that oxidize COD. Or sorry, this is an error. This is the microbial yield from, we've got Y sub N, which is the microbial yield from nitrifying microorganisms that are oxidizing ammonia nitrogen. And we didn't show the calculations for this in the previous slide, but it would be done the same way as when we calculated the 0.45 grams of ESS per gram COD, only with the nitrification stoichiometry. So this is typically assumed to be 0.15 grams of ESS per gram of ammonia nitrogen oxidized. We've got S sub 0, S naught, and S, which are the influent and effluent biodegradable COD concentrations, expressed in milligrams per liter or grams per cubic meter. We've got NOx, which is the concentration of ammonia nitrogen that's converted to nitrate. So it's the milligrams per liter of ammonia that's converted into nitrate. B sub H, which is the endogenous decay coefficient. It's basically the die-off rate for heterotrophic microorganisms. It's typically assumed to be 0.12 days to the -1. That's at a temperature of 20 degrees, but it's temperature dependent, so you can estimate it at other temperatures if you have hotter or colder conditions using this equation right here. B sub N, likewise, is the endogenous decay rate coefficient for nitrifying microorganisms. It's typically assumed to be 0.17 days to the -1, and again can be modified based on the temperature. The fraction of biomass, F sub D, which remains as cell debris, is usually assumed to be between 0.10 and 0.15 grams of ESS per gram of biomass depleted by decay. And the last term here, SRT, is the solids retention time in days. All right, so we're going to talk about SRT a lot throughout the rest of the semester as this master design variable, which controls the efficiency of activated sludge processes. And you can see that SRT is involved in each of the 3 terms of this equation right here. So it's a very important parameter in terms of the amount of sludge that's produced in the system. Another important equation to apply during the design of biological treatment systems is the oxygen transfer rate. All right, so SOTR, which is the standard oxygen transfer rate for a clean water source. So we're bubbling air into the wastewater. If that wastewater was completely clean, there's an oxygen transfer rate that is rated for the aerator itself. However, for wastewater, the oxygen transfer rate is a little bit less efficient because of the organic materials and the biofilm and other factors that affect the actual oxygen transfer rate. It needs to be corrected for field conditions. That means also temperature and elevation. So this is the one, the OTR, this is the oxygen transfer rate that should match what you calculate as your oxygen demand. All right, so this oxygen demand, which is required, should be the one that's the same value that's supplied by your aerators. And we need to correct this value for the conditions of the wastewater, which is what this equation is for. Once we get the standard oxygen transfer rate, we can compare that to the ratings provided by oxygen diffuser suppliers. All right, so the terms of this equation here are defined below. Alpha is the oxygen transfer correction factor. It's the relative transfer rate for clean water compared to wastewater. And so if we have an activated sludge system without nitrification, we would use a value somewhere between 0.3 and 0.5. If we have a system where we're trying to achieve nitrification as well, that value would be somewhere between 0.5 and 0.75. F is the fouling factor for diffusers. We have 1 for no fouling, but we usually assume that there's some fouling over time. So we would use a value between 0.65 to 0.90. Beta is the saturation surface tension correction factor. We usually assume a value of 0.95. P sub A and P sub B are the pressures. So P sub A being the standard pressure at sea level, which is 10.33 meters of water pressure head or 760 millimeters of mercury. P sub B is the pressure at the treatment plant site based on the elevation. All right, so if we were to construct an activated sludge system at sea level, it's going to perform differently in terms of oxygen transfer rates than if we were to build it up in the mountains, where we have lower pressure and less oxygen transfer. And we have to correct for that by using this ratio of P sub B over P sub A. C prime S at temperature T is the saturated DO concentration at sea level and at operating temperature. C prime S at 20 degrees is the saturated DO concentration at sea level and at a standard temperature of 20 degrees. So also, again, we're correcting for the effect of temperature. C residual is the residual oxygen that we want to maintain in the aeration basin. So we don't want the oxygen to be completely depleted. We want to leave residual concentration, maybe 1 milligram per liter, 2 milligrams per liter. All right, and we're going to include that in this calculation. And then C prime infinity at 20 degrees, this is the DO concentration at 20 degrees Celsius, which is corrected for the pressure of the diffuser in the basin. And we use this equation here. So this term here, which goes on the top of this equation on the numerator, this is calculated as C prime standard at 20 degrees times 1 plus DE times the ratio of DF over PA, where again, PA is standard pressure at sea level, D sub F is the depth of diffusers in the basin, and D sub E is the mid-depth correction factor. We're typically using a value of 0.4. It can vary between 0.25 and 0.45. So what is this term accounting for? This is basically, we've got our pressure, which is affecting oxygen transfer, right? And if, again, we talked about how you have a different air pressure at sea level than you do up in the mountains. So you need to correct for that factor. However, what this is about is also correcting as well for the pressure that's experienced at the depth where your aerators are placed. So you know that if you go deeper into water, there's an increase in pressure because the water above the aerator is providing a higher pressure for what's experienced at the bottom of the aeration basin. So we need to account for that increase in pressure based on this approach right here, this depth of diffusers in the basin. All right, and then as the air bubbles rise up to the top, that correction factor D sub E is accounting for the fact that the pressure decreases. So you've got higher pressure, more diffusion at the bottom of the basin. You've got lower pressure and less diffusion as you rise up, as those bubbles rise up to the top. All right, here's a table and some equations that are going to be useful for performing these calculations of the standard oxygen transfer rate. And you can see here, we've got the calculation in SI units and US customary units. So this is the change in atmospheric pressure with respect to elevation. So this is to find that P sub B and that P sub A, which here it's written as P sub S, but it's the same thing, atmospheric pressure at sea level. So we can calculate the pressure at elevation Z, whatever your elevation is, with respect to the atmospheric pressure at sea level using these equations. This table up above here shows the air solubility of oxygen in milligrams per liter as a function of temperature and as a function of the elevation in meters. So if we have a site where we're building a wastewater treatment plant that's at elevation 1000 and it's operating at a temperature of 10 degrees, this 10.011 is the milligrams per liter of oxygen, basically the saturation concentration of oxygen at that temperature and at that sea level. All right, and that changes as you increase the temperature, the amount of oxygen that you can get into the wastewater decreases. And as you increase the elevation, same thing, you have less pressure, so the maximum concentration of oxygen that you can get into the wastewater decreases. All right. So once we determine what the standard oxygen transfer rate is for our diffusers, we now can make calculations to determine what volume of air is needed to supply to the system, like how much our pumps have to deliver, and also the energy requirements based on the transfer rating, the oxygen transfer rating of a pump. So this helps us estimate what our energy costs of a wastewater treatment facility are going to be, and also determine how many pumps and what size pumps we need to specify for the design. All right, so oxygen transfer values for aeration devices are usually published by manufacturers. So if you're shopping around for an aerator, depending on the aerator type, the supplier should be able to give you the oxygen transfer value, the oxygen transfer rating, which is the pounds of O2 per horsepower per hour, as well as the oxygen transfer efficiency, which is expressed as a percentage. So in general, fine bubble diffusers tend to have transfer efficiencies between 20 and 39% with transfer ratings of 4 to 7.7 pounds of O2 per horsepower per hour. Coarse bubble diffusers, on the other hand, have slightly lower transfer efficiency because the bubbles are larger, and they have a lower transfer rating as well. All right, so you choose your aerator type, you estimate the amount of energy required and the flow rate of air needed. So the terms in this equation are all defined here. The oxygen transfer rating, the SOTR, which we talked about before. For the second equation, we already know the SOTR, the oxygen transfer efficiency, which is supplied by the manufacturer or can be assumed based on the type of aerator being used. Rho sub air, this is the density of air. So that's usually assumed to be equivalent to 1.29 kilograms per cubic meter, which is the same as approximately 0.08 pounds per cubic foot. And then F sub O2, this is the percent of oxygen in air. Technically, this can be corrected for elevation and other factors, but we typically assume a value of 23.2%. We represent that as a fraction, 0.232. So this would be assumed to be equal to 1 if you're using pure oxygen. So there's some facilities that instead of pumping air into the aeration basin, they have pure oxygen tanks stored on site, and they're pumping 100% oxygen into the system. So obviously that's going to be more efficient, but there's other trade-offs associated with the use of pure oxygen at wastewater facilities, like safety concerns associated with storing pure oxygen. But that's what this term is. So with these two equations, again, you estimate the energy requirements and the air supply requirements.
Okay, let's do another example problem. So let's suppose that we have floating aerators, 10 horsepower each, with an oxygen transfer rating of approximately 1.3 kilograms per horsepower hour, and that they're going to be used for a BOD reduction in an aeration system for a wastewater treatment plant located at sea level with a capacity of 1 million gallons. That would be the volume of the basin, a flow rate of 0.5 million gallons per day, an influent BOD of 180 milligrams per liter, and an effluent BOD of 50 milligrams per liter. There's no recycle flow, and the system does not nitrify. There is a residual DO of 5 milligrams per liter. You can assume that the average water temperature is 15 degrees Celsius, and use the values shown below for alpha, beta, and F, the F factor. So this example is to calculate the oxygen demand and determine the number of aerators required for this system. Alright, so to solve this example problem, we start off with these two equations here. And since in the problem statement we're told that there's no nitrification in this system, we can essentially ignore the third term of both equations. So we have to calculate the value of px bio before we can calculate the oxygen demand. And since we can ignore the nitrifier biomass, we really just have two terms here. The first thing we need to do is list out all of the assumptions for the variables in this equation. So if we plug in those values, to the px bio equation, you can see here that we get a value of 113,191 grams of VSS per day, which is equivalent to approximately 113 kilograms per day of sludge. So now that we have that value, we can plug it into the oxygen demand equation using our flow rates and our BOD concentrations coming in and leaving the system, and of course converting between grams of VSS to grams of oxygen using our value of 1.42. And we get a value for oxygen demand equal to approximately 135 kilograms per day. So now, using that value, we can calculate SOTR, which is the standard oxygen transfer rating needed in order to determine our aerator requirements. So here's the equation for SOTR. So OTR is the value that we calculated in the previous step, and that value is adjusted by three different factors. The first one is the factor that adjusts according to fouling of the aerators. The second term here is adjusting based on the relative difference in temperature and elevation and oxygen concentrations that vary according to those two parameters. And the third term here is adjusting for temperature. So we need to first start out by listing all of the assumptions for the different variables in this equation. So we already know the values of alpha, the fouling factor, and beta. For CS at our temperature of 15 degrees Celsius, we can look it up in the table provided in the slides, and we can find a value of 10.084 milligrams per liter at sea level. For CS at 20 degrees and also at sea level, the concentration of these are the saturation concentrations for dissolved oxygen. So at 15 degrees, 10.084 milligrams per liter, but at 20 degrees, it's 9.092 milligrams per liter. The next term here, PB over PA, this would be adjusting for differences in altitude and the effect that that has on oxygen concentrations in water. And since we're told that this system is approximately at sea level, you'll find here that this equation ends up being equal to E raised to the 0, which is equal to 1. So essentially we don't need to correct for altitude if our system is close to sea level. But if we were to use this approach for a system that's located above sea level, we would use the standard values for G, the gravitational constant, the grams per mole of air, 28.97, and then our standard values for R, our temperature, as well as the elevation at the site relative to the elevation at sea level. All right, and for C infinity at 20 degrees, we have the value 9.092 milligrams per liter, and normally we would correct for the depth below the surface of water where the aerator is going to be installed, and that would influence the concentration of oxygen at that depth. However, in this case, these are surface floating aerators, meaning that the depth is 0, and this term really does not apply. It's just equal to 9.092 milligrams per liter. And finally, we're told that the residual oxygen concentration is 5 milligrams per liter. So now that we've established the values of all these parameters for our equations, we can calculate the first, second, and third terms of our SOTR equation. So you can see here in the calculations that the first term is equal to a value of 3.33. The second term is calculated to be a value of 2.23, and the third term is calculated to be a value of 1.13. So now we multiply our oxygen demand, 135 kilograms per day, by those three terms in order to get the standard oxygen transfer value. So that, as you can see here, is equal to 1,133 kilograms per day. Next step is to calculate the energy needs. So our energy equation takes the SOTR value and divides it by the oxygen transfer rating of the aerators that we're using. So we saw from a table in the previous slide that for floating aerators, these values tend to range between 2.0 and 3.6 pounds per horsepower hour, or 1.2 to 2.2 kilograms per kilowatt hour. Now we want to get the value in horsepower using the energy equation, but we also have our SOTR value in kilograms of O2. So we need to use a oxygen transfer rating that's expressed in the units of kilograms of O2 per horsepower hour. So if we assume 1.8 kilograms O2 per kilowatt hour, that's equivalent to approximately 1.3 kilograms per horsepower hour, and that falls right between that range provided in the table from the previous slide. So now, implementing the energy equation, we take the SOTR, 1,133 kilograms per day, divided by that transfer rating, 1.3 kilograms per horsepower hour. We need to convert the units between hours and days, and all the units cancel out, leaving us just with horsepower, and that gives us a total horsepower requirement of 36.3. So since each of our aerators have 10 horsepower rating, that means we need at least 4 of them in order to meet the oxygen demands of our system.
Let's do another example problem. So here we have a fine bubble aeration system at sea level, which is used to remove BOD, and it's also fully nitrifying the wastewater. So full conversion of ammonia nitrogen to nitrate. The temperature of the wastewater is 18 degrees Celsius. The depth of the diffusers, the air diffusers, is 18 feet. We have a chloride concentration of 5,000 milligrams per liter and a residual DO concentration of 2 milligrams per liter. What is the oxygen demand? What's the total horsepower requirement? And how much airflow do we need if the influent wastewater flow rate concentration is 140 milligrams per liter primary effluent, so that's the concentration coming into the aeration basin. Leaving the aeration basin, the concentration is 15 milligrams per liter, and we have a total of 23 milligrams per liter of ammonia, which is being converted to nitrate. We can assume alpha equals 0.65, beta equals 0.95, and the fraction F equals 0.75. For the F factor, sorry, for fouling equals 0.75.
All right, here you'll find the solution to example 3-14, showing the calculation of the oxygen demand based on the value of px bio, and then the calculation of SOTR based on the oxygen demand, and then finally the calculation of the energy requirements, 80 kilowatts, and the flow rate of airflow, which came out to be 74,900 cubic meters per day.
All right, after aeration, the next process in the system is typically secondary or final clarification of the wastewater. So now we've reduced the concentration of COD in the aeration basin already, but we still have a high solids concentration, and that's mostly due to the biological growth. We've got biosolids, biomass that is now in this wastewater, and it has to be removed before we can proceed either to the next step in the treatment process, which might be tertiary treatment, or to disinfection if that's necessary, or to discharge back to the environment or reuse. All right, so the purpose of secondary clarification or secondary settling is to remove those, that biological growth, to remove that microbial biomass, to clarify that liquid effluent. We use gravity separation of the biological growth. It's more difficult in the secondary clarifier than it is in the primary clarifier. And the reason is that the activated sludge process in the aeration basin creates flocks, solids materials that are lighter and they're more buoyant. So they take a little bit longer to settle out to the bottom. They're a little bit harder sometimes to get good settling properties of that sludge. And a good operator will know how to manipulate the return sludge rate, or to manipulate the solids retention time and the way the system is operated in order to achieve a good mix of flocks of microbial biomass that produce flocks that are easily settlable in secondary clarifier. All right, so another reason that these are tough to remove in secondary clarifiers is that the microbial production, these microbes are producing gas bubbles, CO2, and these are lifting, these gas bubbles can lift the tiny flocks to the surface, kind of preventing them from being able to settle down. All right, but again, a good operator is going to know how to tweak the system in terms of the solids retention time and the return sludge rate versus the waste sludge rate in order to optimize the types of flocks that are being produced and to get flocks that have good settling properties. All right, so to design secondary or final clarifiers, we use the same approach as we did for primary clarification, right? We're still calculating the hydraulic retention time as the volume divided by the flow rate. We're still using an overflow rate, which is the flow rate divided by the surface area. We're still calculating a weir loading rate, Q divided by the weir length. And we're also usually checking the solids loading rate, which is the suspended solids concentration times the flow rate divided by the area. And we've got some typical design values, again, that you can see in this table that are used for secondary clarifiers, and you'll note that those are different than what we use for primary clarifiers. So for, depending on the type of treatment, if we've got settling after air activated sludge, or if we've got settling after activated sludge with pure oxygen, we might use some different values. Extended aeration systems use different overflow rates as well. And you can see the ranges here, right? If we're also trying to achieve phosphorus removal, which might be a goal for some wastewater treatment plants, then we might modify the overflow rates in order to optimize for phosphorus removal as well. All right, so you can use these values to make sure that your design approach is within line, within the range of typical values for secondary clarifiers. But this is another area where you're going to want to consult the design guidelines to make sure that you are complying with the overflow rate and solids loading requirements if stated.